Assalamualaikum warahmatullahi wabarakatuh. Hello guys, today I hope you all are well. Because of the COVID-19 pandemic, we all are encouraged to study online, including me. Because of this, I was given an assignment by my lecturer to make a video about our learning. Alright, today I was given the task for making more videos from my lecture about equilibria in non-ideal system, more precisely about activities and reaction equilibrium, activities and electrolytic solution, the Debye-Huckel theory of the structure of dilute ionic solution, and equilibria in ionic solution. Okay guys, stay at home, stay healthy, enjoy to my video. Don't forget to like, comment, and subscribe. First, I will explain about activities and reaction equilibrium. The practical system is more commonly used. The condition of equilibrium becomes delta G equal minus RT ln Ka, where delta G is the standard Gibbs energy change, and Ka is the proper quotient of equilibrium activities. Since delta G is a function only of T and P, Ka is a function only T and P, and is independent of compensation. Since each activity has the form A E equal gamma A M A, we can written Ka equal K gamma Km, where K gamma and Km are proper equations of activity coefficient and of molalities respectively. Since the gamma s depend on composition, so that Km depends on composition. In dilute real solution, all the gamma s approach unity, K gamma approaches unity, and Km approaches Ka, except when we are particularly interested in the evaluation of activity coefficient. We should treat Km as if it were independent of composition. Doing to incredibly simplifies the discussion of equilibria. Okay, next I will explain about activities in electrolytic solution. The problem of defining activities is somewhat more complicated in electrolytic solution than in solution of non-electrolyte solution of strong electrolytes exhibit marked definition from ideal behavior even at concentration will be below those at which a solution of a constant non-electrolyte would behave an ideal dilute way. The determination of activity and activity coefficient has a correspondingly greater importance for solution of strong electrolytes. For simple the notation, as much as possible, a subscript will be used for the properties of the solvent. Symbol without subscript refer to the solute, subscript plus and minus refer to the properties of the positive and negative ions. Consider a solution of an electrolyte that is completely dissociated into ions. by the additivity rule, the Gibbs energy of the solution should be sum of the Gibbs energies of the solvent, the positive and the negative ions. G equal n mu plus mu plus n minus mu minus. If H mole the electrolyte dissociated into P plus positive ions and P minus negative ions, then N plus equal P plus N and N minus equal P minus N, where N is number of mole of the electrolyte in the solution. Equation becomes G equal N mu plus N P plus mu plus P minus mu minus. If mu is the chemical potential of the electrolyte in the solution, then we should also have G equal N mu plus N mu. Table for mean ionic activity coefficient of strong electrolytes. Okay, next about the Davy-Huckel theory of the structure of dilute ionic solution. At this stage, it is worthwhile to describe the constitution of ionic solution in some detail. The solute in dilute solution of non-electrolytes is identically described thermodynamical by the equation mu equal mu plus RT ln M. The chemical potential is sum of two terms. The first mu is independent of composition and the second depends on the composition. Equation above is fairly good for most non-electrolytes up to concentration as high 10 times 1 m, and for many other it does well at even higher concentration. The simple expression in equation above is not adequate for electrolyte solution. Deviations are pronounced even at concentration of 0.001 m. This is true even if equation above is modified to take into account the several ions produced. Okay, next about equilibria in ionic solution. From the Davy-Huckel limiting law equation, we find a negative value of in gamma plus minus, which confirms the physical argument that the interaction with other ions lower the Gibbs energy of a ionic ion in the electrolytic solution. This lower Gibbs energy means that the ion is a more stable solution than it would be if it were not charged. The extra stability is measured by the term Kt ln gamma plus minus. In the expression for the chemical potential, now we examine the consequences of this extra stability in two simple cases. The ionization of a weak acid. the solubility of sparingly stable salt. Consider the dissociation equilibrium of a weak acid Ha H plus A minus. The equilibrium constant is the quotient of the activity. K equal A H plus A minus divided A H A. By the definition we have A H plus equal gamma plus N H plus. A equal gamma minus M A minus. A H equal gamma H M H. So that K equal gamma plus gamma minus divided gamma H. M H plus M A minus equal M H equal gamma rank 2 plus minus M H plus M A minus equal M H. Where we have used the relation gamma plus gamma minus equal gamma rank 2 plus minus. If the total molality of the acid is M and the degree of dissolution is A, M H plus equal M, then K equal gamma rank 2 plus minus A alpha rank 2M divided gamma HA 1 minus alpha. If the solution is dilute with many, set gamma HA equal 1, since HA is a uncharged species. Also, if K is small, 1 minus alpha, then alpha equal K divided M rank 1 divided 2, 1 divided gamma plus minus. If we ignore the ionic interaction, we should set gamma plus minus equal 1. The calculate alpha 0 equal K divided M rank 1 divided 2. Then becomes alpha equal alpha 0 equal gamma plus minus. Consider the equilibrium of a slightly soluble salt, such as silver chloride, which it is ion AgCl, Ag plus Cl mean. The solubility product constant is KASP equal AAG plus ACl equal gamma plus M plus gamma minus M minus. If SA is the solubility of the salt is mole per kilogram of water, then M plus equal M min equal S, and KSP equal gamma rank 2 plus minus S rank 2. If S0 is the solubility, calculate ignoring ionic interaction, then S0 rank 2 equal KSP, and we have S equal S0 divided gamma plus minus, which show that the solubility is increased by the ionic interaction by the same reaction is a way use the discussing the dissociation of the weak acid. We can show that in 0.1 molar solution of its inert electrolyte such as KNO3, the solubility would be increased by 125. The insolubility produced by the inert electrolyte is called salting in. The effect of an inert electrolyte on the solubility of the salt such as BaSO4 would be such a large because of the large change charge of the B ring 2 plus NSO4 ring 2 minus ion. The salt effect of solubility produced by an inert electrolyte salt not be confused with the decrease in solubility effect. The by electrolyte, the constant ion in common with the sparingly soluble salt. In addition to acting in the opposite sense, the common ion effect is enormous compared to the effect of an inert electrolyte.